Welcome to the video. We have seen a typical file structure, and we have studied basic components such as runner, experiment, callbacks. Two previous videos have introduced a catalyst configuration file structure. Now, let's take a look at the real example. Here comes cifar 10 classification task. You can find this example in Catalyst example folder on GitHub. Firstly, clone Catalyst repository and go to the examples folder. The command catalyst-run starts training. This command requires a config parameter, which specifies a path to the configuration file. If we choose the verbose option, Catalyst will write the logs into a console. The example folder has 4 familiar files and a readme.md file for GitHub documentation. Now you see a basic hierarchy. To start training, point a configuration file. This configuration file has exp_dir parameter. The parameter instructs the framework where to search for init.py file. exp_dir points to a cifar simple folder because the working directory is the examples folder. The catalyst imports init.py. The library gets the symbol runner from the module. This symbol must be a child class of runner. If you use deep learning, it should be either supervised runner or 1DB supervised runner. In case of a need, you are able to create a child class of supervised runner. Then override several methods and import your class with the alias runner. Within our example, we import supervised runner from Catalyst. Catalyst will create an instance of supervised runner later. For an experiment, the logic is the same. As far as each experiment has its own datasets, augmentations, and transformations, it's highly recommended to create your own subclass most of the time. Well, we do use config API. Therefore, our experiment class is inherited from config experiment. We import the experiment class into init.py. This action instructs the library to create an instance of the experiment later. We import the model into init.py to register it in Catalyst registry. When the model is imported, it will be registered automatically thanks to a decorator system. The next slides will provide additional information. We have studied Catalyst configuration file structure. Let's have a practice. In the model params section, we define a model and its arguments. Our registered simple net is used without arguments. exp_dir in args section introduces a folder which contains init.py. logdir sets a folder for logs, checkpoints, and code dump. Stages section introduces the settings for all stages. Let's suppose you desire to change the settings for a specific stage. Then you should add your stage section to the stage's parent section. We see this scenario here. Data params, state params, criterion params, scheduler params, and callbacks params are common for all sections. Optimizer params is specific for the stage 1. Batch size and num workers are the parameters for PyTorch data loader. Num epochs set epoch count in the stage. Main metric is a metric to choose the best checkpoint file. The framework performs one epoch of training and validating. Then, Catalyst decides whether this epoch has better metrics on a validation set. If you set minimize metric to false, then the higher the metric, the better the checkpoint. Accuracy 01 is produced by accuracy callback and is put into runner state. Please note the anchor with a name reduce metric. This anchor is used by scheduler callback. You can see it below. Checkpoint data contains information that will be written to each checkpoint. You can add an arbitrary count of parameters here. Criterion specifies a loss to minimize. Scheduler controls the learning rate during training. Here, we choose the registered class multi-step LR, milestones, and gamma. They are the options to transfer to the multi-step LR constructor. In the same manner, you can pass parameters to your model, optimizer, callback, and criterion. As we have studied, callbacks process events during training. Criterion callback takes model output from runner state, calculates the loss, and saves it to runner state. Then, optimizer callback reads the loss from the buffer and changes the weights. Please remember, we declare the loss and the optimizer in other sections, and the callbacks apply them to perform training. Accuracy callback takes predictions and targets from runner state and computes accuracy 01, accuracy 03, and accuracy 05. Then, the callback saves them in runner state. Later, another callback can take this information from runner state and process somehow. For example, a callback may log all metrics to 1DB service. Schedule callback invokes the scheduler that controls the learning rate. Reduce metric is replaced here by the anchor's value from the main metrics section. Checkpoint callback saves and loads model weights in logdir checkpoints folder. Finally, in stage 1 optimizer params section, we choose an optimizer for the stage. We have chosen SimpleNet in our configuration file. However, this is not a standard model and we need to register it manually. Let's review two methods to register a custom model. Variant number 1. We wrap the model class with the decorator catalyst contrib registry model. All we need to do in init.py is to import the model. The variant is shown in the example. Variant number 2. We register our model manually in init.py. We use the same method as for the decorator in the first variant. There is one component we need to clarify. The main task of an experiment is to realize the getDatasets method. This method should return a dictionary with the train-valid datasets. You may also need to realize the getTransforms method. Obviously, this method may be used in your datasets. There are two methods to return values from your dictionary. In the first variant, the dictionary returns a tuple of objects. The left object is saved in the key features. The right object is saved in the key targets. In the second variant, you return a dictionary with explicit names. An advantage of this approach is the ability to return an arbitrary count of objects. Congratulations! We have studied the cifar simple example. Thank you for having watched the video. In the following one, we will debug the cifar simple example in PyCharm. It will give you a comprehensive understanding of how the framework processes the components. See you next time!